Hello, I'm Nancy Respieza, and I'll be giving a 2-minute talk on the classification between machine-translated text and original text by part-of-speech tagging representation. I'd like to make a quick note that the task I'm addressing is nothing unique, but we'll be using less conventional methods for this task. First, that idealistically, more information is better if we're disregarding physical constraints like computation and time. But we cannot, so we should consider what is necessary to be a feature. For this binary classification task, we can generally say that we don't need the context of words. We do care about the sequences of words, which should indicate that we'll be using engrams. Part-of-speech tagging is a way for English words to be categorized into finitely many classes. The dataset is from the NLTK library, sourced from Project Gutenberg. The Pentry Bank POS tag table contains 36 POS tags. Our data has 34 POS tags, and we're looking at a naive 39,304 permutations. As one-hot encoding vectors, this is large. The dictionary search is doable, but namely because of the small number of POS tags. Now, like most n-gram language models, distribution is sparse, but isn't necessary for this task. Consider the graph, which is a histogram of the unigram frequency of the training data. This is Zipf's law. This graph should look familiar, so we can model it as 1 over x. We can apply an integration and manipulate the equation such that we can lower bound a percentage of data by an index. We set a lower bound of 90% of the unigram, giving us a naive permutation of 13,824. Additionally, we can model under a similar function, but this is a hyperparameter. Now, it's important to mention that we do lose data. We do lose dimensions that may be distinguishable, but previous sparse permutations may no longer be sparse and may be enough for the task. Here are the options that we use as the embedding layers. Here we have our baseline performance accuracies on the left, and on our right we have our embedding layer performance accuracies. All of the architectures are the same except for the word embedding layer. Additionally, we want to reason our results, so we use paired and unpaired t-testing, and retrain the models, testing on a fixed test set. Conclusively, we have seen the impact of a dense word embedding on time. We have also failed to reject the null hypothesis between embedding 1 and embedding 2. We have statistical significance between the other embedding layers, but this does not quantify the impact. As a takeaway, modeling data distribution is useful for dimensionality reduction. And these are the references.